Welcome everybody. I'm very happy to see you all. Just a quick question. How many Italian do we have in the room? Okay, I leave. On how many non-scientists? Okay. I will welcome. It's first event for this series called Waiting for Pin 22. It's an initiative of Lavinia. And our thing, just before we jump into the events, is just to give you what is Pint of Science, because it's still new for a lot of people. So this is the perfect illustration of what is Pint of Science and what is behind. So actually, we have this is Barney. This is a mascot, and we have one handmade from Oslo. I don't know where it is now.
It's downstairs.
Okay, so it's alone downstairs. And normally, Pint of Science is to host a festival in all over the world, so it's 30 countries nowadays, and we bring local scientists in bars, so normal people, non-scientist people, can come and listen to it. So the speaker make the effort to give a presentation in engaging way, so everybody can understand. And so that would be so. Of course, this event we can't be possible without the speakers, but as well the volunteers. Lavinia will represent who they are in Oslo. And as well, it's like there's a lot of game. On that, we have more information. So Pint of Science is born in 2013 in UK, and since it has been exponential growth until COVID. And in Norway, we have been the good idea to start before COVID. So yeah, immediately. Yeah, October, yeah, so we have been clever. So the two first festivals were online, digital. We managed to have a lot of people, and now we are back in bars. So we are present in 5 cities in Norway. So Tromsø, Trondheim, Bergen, Stavanger, and Oslo, who are the biggest team. You can find us in every social media you use. So we are present in Facebook, LinkedIn, Instagram, YouTube, and even LinkedIn. And we have a website, and we have also a newsletter, so you can as well register. And yeah, that is your turn now. Thanks.
It's a little bit tricky. Thank you, Thibaut. I don't want to be long. I just want to introduce the team of volunteers that is working in Oslo, and I want to thank all of them, and in particular those that are putting a lot of efforts in the organization of these collateral events. And so Thibaut, of course, but also Elisa, that will chair the night today. Praveen, that is helping with all the technical stuff, and just give him the word for a few moments.
Hi everyone, I'm very happy to be part of the Pint of Science, and I'm very excited to have you in person. And also, like, one important thing is, like, we are streaming in YouTube, so you can have a nice time there. Thank you.
Thank you, Praveen. And for those who are following the streaming, remember that you can ask questions to our speakers, just writing them down in the comments. And Lourdes, that is managing the quiz. Please.
Hello, everybody. Glad to see so many people that show up here. And my name is Lourdes, Lulu, you can call me. And tonight I will be hosting the quiz. So I will talk to you soon. And hope you guys have fun.
Thank you. And to play with us, just you can download the app of Mentimeter, or you can work directly online, and use the code that you can see here. But you will also see them. You will also see it later. And last but not least, Agnieszka, who is working on the advertisement and the social media. Of course, a big thank you to our speakers, because without them, this night would not be possible. So thank you very much, because they are giving us their time and their expertise. And this is, of course, very important, and it's a big work. But of course, this night would not be possible. Without the support of our co-hosts. This night is hosted by the Italian Institute of Culture and by the Italian Embassy, and I'm very glad to invite here the Italian ambassador, Alberto Colello.
Thank you so much for inviting me. Thank you so much for this very nice initiative. I'll tell you a story how this meeting was born at the embassy. We got an email from Lavinia at the general email address of the embassy, and the mail stayed a couple of days in the box because basically the people who read it didn't believe it was a serious stuff, you know, beer, pint of beer, science. So somebody told me, no, Ambassador, this is fake news, you know, this is some spam, it's not serious. But then I remember I read all the email and then I liked the idea. I said, oh, okay, why not? So I called her the day after, and in a couple of days we decided to start this adventure. So it's very nice. Since we talk about science tonight, I would like also to give you some numbers, some figures. Since we are doing the question and answer, I have a question to ask you. Guess how many Italian researchers and scientists live and work in Norway? 1 to 50, 50 to 200, 200 to 1,000. They are 500. According to the Norwegian Council of Research, today around 500 Italian scientists and researchers live and work in Norway, which is an interesting information, also given that the overall Italian community around 10,000 people. So out of 10,000 people, 500 are scientists. And this, you know, it's important. Of course, we are proud of this number. From the other side, the downside effect is that you are many brains, Italian brains, who are fantastically educated, trained in our country, and then given for free to a different country. So this is a sort of brain drain, and we should think about this. We at the embassy, since a large part of the community is made out of scientists. Actually, another information. Many people ask me why what are the reasons why? What's the main motives, the motivation why there are so many Italians living in Norway? And of course, you know, the first reason is love, because Italians, they get in love with Norwegian men or women. So we calculate that around 55-60% of the Italians living in Norway, they are here simply because they got in love there. But the second most important reason is probably research, science, and this means also that, if I can say so, the average quality of the Italians living in Norway is very high. If you look at the figures also, another information, 65% of the Italians living in Norway have at least a higher education, at least university education or up or higher. So that means, while in Italy only 18% of the Italians got a university degree or a master's degree. So that means that in Norway you are 3 times, 4 times more educated than the Italians living in Italy. That's very interesting. Okay, to finish, 2 information. Since there are so many researchers, we try to work a lot with them. We have 2 initiatives which are going on right now, and they are very important. One is an initiative by the Italian Council of Research on mapping and especially getting to know the reasons why and the characteristics of the Italian researchers abroad. If you go to the embassy website, you will find the link where you can answer this questionnaire, and at the end of the story there will be a sort of investigation survey on the characteristics of the Italian researchers in the world, all over the world. And a second initiative is very interesting. We have a portal for communication, for connection among the Italian researchers in the world. It's called innovitalia.net, Innovation Italy, Innovitalia. Again, if you go to the embassy site, you will find the link to this initiative. All researchers and scientists can register, and you will get a number of information. And so especially, you will get in touch with the network of Italian scientists and researchers all over the world, in addition to information, news, and other update on events, etc. Actually, if you look on Innovitalia, you will find this event tonight, which has been posted by me on the network. So thank you so much, and enjoy the evening.
For hosting this event tonight, and I think we are just ready to start. So I leave the floor to Elisa that will start sharing the night, and I hope you will all enjoy this night of the science here. Thank you.
Scientific event, and I'm very honored to introduce the first speaker, who is Arnoldo Frigessi. Arnoldo is a professor of statistics at the University of Oslo, and is the leader of the Oslo Center for Biostatistics and Epidemiology, and is also director of Big Insight, which is a center of excellence for research-based innovation, which is also a consortium of industry, business, and academia, which tries to develop model-based machine learning methodologies for big data. And as all the rest of the speakers tonight, he's from Italy. And in Italy, he had positions in Rome and in Venice. And then in 1997, he moved to Norway as a researcher at the Norwegian Computing Center. And then he became a professor at the University of Oslo, and also is an elected member of the Royal Norwegian Academy of Sciences and Letters. And tonight, he's going to talk to us about something very, very actual and very important in our everyday life, which is data science for the COVID-19 emergency. So please, stage is yours.
Thank you very much. I use this one, I think. No, I have this one. I need two. Okay, good. Very nice to be here. Thank you for inviting me. I came to Norway 24 years ago. Maybe I was the first of all the Italians who are here. I can tell you what you could not buy in Oslo 24 years ago, that you needed urgently. Then we start to speak about food, I guess, right? And I also have to say that I came to Oslo, as the ambassador told you, as most of you, for love. And I remained here for love, and yes, I also do a nice job. There are advantages here, but let's be frank. So the famous, we don't escape our countries for very strange reasons. Tonight I wanted to introduce a little bit to one thing that I have been doing in the last 2 years that I hadn't thought I would do, which is to use data to understand the COVID epidemics in Norway. I've been involved with the National Institute of Public Health, Folkehelseinstituttet, in producing estimates of the reproduction numbers, the R numbers. We do predictions, and I will tell you a little bit how it has been going on. And maybe if I have time at the end, I also tell you a little bit of what the problems are to do science in a situation of emergency. Science in a situation where the country, the people around you are waiting for results that are important to take decisions that matter. Lots of people have been working with me. Here are some from many different countries. And this is the reproduction number yesterday. So you know what the reproduction number is. The reproduction number R is if you are infected, how many other people will you infect during your period of infectiousness? So if I'm infected and I infect 4 new people, then you see that and then they will also infect 4 more and so on. This would be the reproduction number 4, which was the reproduction number in the beginning of COVID, 4, a bit more than 4. So imagine how rapidly this would explode and how many people would be infected very, very rapidly. If the reproduction number is below 1, then every person infects none or maybe 1 person. So then it's clear that the disease dies out. So this number, the reproduction number, which changes in time, is an important measure of how the situation is now, and therefore also how you think things will develop in the future. So this is time here, and this is 1. It starts in March. This is a week ago. And this is between 0 and 4. This is a reproduction number, how we estimate it every day. Today, the reproduction number is just below 1, 0.96. You're the first one who gets to know it. It's going to be published tonight. And we are statisticians, so we put uncertainty bounds. We are a bit uncertain. They're called confidence intervals. And it says that it's around 1. It's between 0.8 and 1.2. Makes a matter. If it is 0.8, it's much better than 1.2. But we are around 1. And the ability, in fact, that R is larger than 1 is about 30%. So we are in a situation which is stable. So if it continues like this, we will have roughly the same number of people infected every day, the same number of people going to hospital, very stable. And a stable situation, given the level we have today, which is very low, is fine. If we would have a stable situation with a very, very active disease, it would not be fine. Then we would need to take this R down. And the way to take this R down is to make contacts between people more difficult. And this is all the lockdown, the closure, and so on, right? Yeah. So these estimates, we can look to them carefully and understand how things developed in the last weeks. So here is the story from the beginning of July. And this is one here, right? I just blow up that little part now at the end. And you see here that in July, during the vacation time, here is Norwegian vacation time, it was quite fine. It was below 1. People were, when the big contacts, they happen at job and at schools and in transports. And during vacation, there's less contacts in reality, right? And then it came, it went a bit up. Then in August, here, the schools started again. The Norwegian economy starts up again around the 5th of August. And you see how rapidly the reproduction number went up. At that time, the government started to say that it would be possible to meet, the pubs, the restaurants, everything was open again. So we see how rapidly it went up. In the end of August, things started to fall down. This is something quite exceptional that happened because there was no lockdown. Usually we would have seen things like this in the past. We can see them in the past. Look what happened in the very beginning when the first lockdown appeared. A collapse of the reproduction number, right? So this happened only because of testing. So this is because there was massive testing in Norway at that time. You started to get testing in schools, in the Barnehage, in the kindergarten, in the university. Every student got tested twice a week, very often at least. And testing identifies the positives that then are isolated. So this is why the things collapsed. Now it's going up again, as you see, slowly up again. And this is to do with the fact that the society is completely open. We are here.
we didn't need to show that we are double vaccinated. And I'm not allowed to ask if you're double vaccinated, but you all are, almost everybody, depending on age, I guess. But it's going up, and I will tell you in a minute what is happening in England and in other places, what it means for us. But I want to show you a couple of other things that we're doing. So we're doing predictions. So this is a prediction of how many people will have COVID in the next 3 weeks every day. So it will be about, this is about 700 maybe here. So it's, and this is a confidence interval again, but it's going slightly down, right? So it's or maybe it's around 700 every day. So there are 700 new infections number. In the UK, it was 40,000. The tested ones, the ones that have been identified today were, I think, 350. So in our models, we say that roughly half of the infected people are not identified. And it's quite a lot, right? Because these half, they will infect others. They will not isolate themselves. They will go around. Maybe one is here of these 350. Very unlikely, right? But this is what is happening. That the mørketall, they call it in Norwegian, the black number, the invisible part of the disease, is roughly half, which is a problem. And then we predict hospital admissions. That's the most important thing for a government, to make sure that the hospital has capacity to treat the ones that are sick. You know what happened in Italy in the very beginning, when the hospital started to be filled up. That is what is really made every country in the world understanding that this was serious and this was going to happen everywhere. And then hospital admissions, and yeah. You know, I wanted to tell you a brief story about the relations between us scientists and the press in Norway connected to this thing here. So when we make predictions of the next 3 weeks and we say that our number is 1.7, and today there are 100 people in hospitals, in 3 weeks there will be 350. We made often very serious predictions of that type because it was going to explode very, very rapidly. And as soon as we were doing such pessimistic predictions, immediately the government would decide to do something. Or the commune of Oslo would start to do something. They would immediately increase lockdown aspects and interventions. And they work rapidly. So our pessimistic predictions were were never true, luckily, because people were doing things to avoid them. Aftenposten decided to look to how good we were in doing predictions. And they found that we were a disaster. That all our predictions, in particular the pessimistic ones, were wrong. If you understand Norwegian, and you all do, of course, because you all have this norsk kurs, eller et norsk samboer, eller sånn. It took me, I remember that I prepared my first class in Norwegian after 7 years in Norway, and I had prepared it wonderfully, everything written. I was very nervous. This was a double class. In the middle, in the break, the students would come to me and say, you know, you can speak English if you want. Yeah, so it was terrible. But skrekkescenario slår ikke til. Det var feil gang på gang. So the pessimistic scenarios never became true. It was wrong one time after the other. So this shows that, in one sense, we were not able to tell to these journalists of Aftenposten how the things should be understood. We were wrong in our communication. On the other hand, they made no efforts to understand it. We wrote a comment a couple of weeks ago where we said, you do everything wrong and time over time. the discussion finished there. I know I don't have much time, so I will run over a couple of things. I will show you this plot a second to explain you what I and my colleagues are worrying about now. This here is, these dots here are the number of beds occupied by COVID patients in Norway. So today, today it's just around 100, below 100. The blue things are our predictions, and they show that our predictions have been quite good all the time, right? We have been able to guess how many beds were occupied. Occupied beds, very important for the health system, right? But look what is happening here in the very, very last days. So first of all, our predictions are wrong, because we are saying that things are going down. This time they're really wrong, not as Aftenposten is saying, they're really wrong. And because, as you see, the prevalence, the number of people in hospital remains constant, doesn't go down. And we don't understand why. If we look carefully to the same plot now you have to look to the black dots. The same plots now divided by age. So here are, for example, the ones that are my age. I'm in the lower part of the range, 60-69, quite on the lower part. You see here, we see that also here we're starting to do a mistake. So there is a group of patients in hospital in that age that is staying longer than expected. And the children particularly, they're staying longer than expected. For others, it's fine. We don't understand why this happens. And there are 2 or 3 possibilities. One is that one could think that who gets sick now gets really, really sick and needs, because of vaccination and so on, but it doesn't seem to be the case. So we are a bit confused. There might be that some of the parameters that we put in the mathematical models that are behind all this are changing. And I just show you this, and you have to stop me at a certain point. So I've lost I'm changing here. So one thing that we do as part of our to produce this estimate is that we look how long people stay in hospital. So this is when you get symptoms and you have to go to hospital, how many days does it take? And we estimate it to be 8.8 days until May 2020. So in the beginning, doctors didn't know really what to do, and people were in hospital longer than what is now. Now, for example, this number is 8 days, so it has reduced to 1 day. And interesting, in Oslo, it's only 6 days. So it takes less time if you have to go to hospital to reach hospital in Oslo than in other places, because of probably the vicinity of the hospitals themselves, right? So it's easier for a doctor to say, go to Ullevål, instead than if you are in a village up there and you have to take an helicopter to Tromsø, right? Or things like this. But these numbers are changing, and I will jump over all these things. I want to show you this thing here to explain you how is the life of this group of people. We are about 10 statisticians and machine learners, they are called today, data scientists. So we have a very clear routine every week. Monday morning, 7 o'clock, we take the data. So we take the data, and it's the picture until Sunday midnight. And then we have Monday and Tuesday about one day to run these big models on the supercomputers that are in Tromsø, in fact. It's about how many cores? It's about, I think, 2,500 computers that are working for a full day to get these estimates. And then we have other models and do post-processing. So it's a production line. It's a production of results, because at Wednesday, at lunch, everything is done and is produced. I've never worked in such a pressure in my life before. To produce every week a report like this has been a wonderful experience. And we code things. If somebody knows here how easy it is to make mistakes when you write a programming code, yes, I see, yes. Imagine that we are never able to check if we have bugs or not. So everything that we've done has, of course, bugs. So we are hoping that Aftenposten doesn't find them, because then they will be right, of course, right? And I think I have to finish, right? Or I don't know time. I've lost my time things. 5 minutes?
I don't know.
Nobody knows. But then I continue. Then I have 5 more minutes. Okay. In these 5 more minutes, I want to tell you how I think science is changing in a situation of emergency like this. So let's go back to the UK for a second. You remember that Boris Johnson, 12th of March 2020, press conference, he says, we're going to do nothing, right? UK is going to do nothing. It's going to go fine. We wait for the famous herd immunity. 2 days after, the 16th of March, 3 days after, the Imperial College, Neil Ferguson, a very famous statistician doing infectious diseases, he published a report on the web where he shows one plot, which is this one. If you do nothing, 500,000 people are going to die. And if you do everything, 20,000 will die. And 1 day after or 2 days after, he changed his mind. And if you want, this is not bad that a politician is able to change her or his mind, right? You wonder why he had this previous decision, and you wonder what are the decisions he's taking now. But this is important, and this is an immediate impact of science. This is science. This is Pint of Science, right? So this is science that has an immediate impact, which also shows how important it is to be relevant and in time. If this report would have come 6 months after, it wouldn't have been very important, right? We do lots of mistakes, not only bugs, and everybody does mistakes. We have on our web, we have a document that is growing page after page, where we change hypotheses, adapt our assumptions, understand better the disease, always changing. So interesting, as a scientist, I am very often not coherent with myself. I change my mind. I have to tell you, what I said yesterday, sorry, I was wrong. Every scientist suffers terribly when you say something like this, right? Not only the scientist, also my mother suffered terribly like this, yes. She's 90 and I think she's still not. 2 minutes. I stopped to speak about my mother now. Okay, so UK situation. Yesterday, the government said that they will continue to keep everything open, even if the situation is really deteriorating dramatically. They don't have a plan B, they say. This is how it looks. Here you see the number of cases per 100,000 people for the UK, for Norway, and for Italy. The situation in the UK is growing very clearly. We are completely stable and very low, but you see Norway had a trouble as we saw before in August. So what is happening here? It's and every government all over the world is worrying about this. Draghi yesterday was saying, the Italian Prime Minister, he was saying, look to the UK. You can't just jump into the normality. We have to do it slowly, right? And he has absolutely right. I mean, this situation comes probably from a complete normality that is back in the UK. Yes, and the other reason is that the UK was the first country in Europe that started vaccinating about 3 months before Norway and Italy, because they had their own AstraZeneca. They were very proud of this. Yes. AstraZeneca is probably not the best of these vaccines, and it fades more rapidly. So it can well be that the UK population today is not protected as well as the rest of Europe. There is research that says that the protection is maybe only 50% in the UK now. In Norway, we think it's about 85. if you take the vaccinated population. So there's a big difference. And this is also in Italy very similar, I have to say. So I conclude by telling you that being a scientist in this terrible period has been, in fact, quite interesting and rewarding. It was tiring, it was depressing, and it was sometimes very challenging. But I have to say that I'm very lucky that I have been able to work in this environment. Thank you very much.
That's okay. Questions?
How can the prediction take into account things that are very difficult to predict, like people going on holidays or people just changing their habits? How can you predict that?
This is a very important point. So our predictions are short term, 3 weeks. We cannot do longer predictions because things are changing much more. But in 3 weeks, things are not changing too much. And we do predictions always under the assumption that nothing changes. So we are not saying that we see a trend, for example, and something that goes down, and then we continue to make it go down more and more. No, we keep it fixed. And this is one way of doing predictions. You can do many. You could call it simulations of the future under the current conditions. We think this is an important instrument because it tells you what would happen if you don't do anything, right? And long-term predictions are different. Then you make even stronger assumptions because nobody can predict how people are behaving.
I have a question.
Yeah.
So the R number. Okay. Yes, it's like index of reproducibility. Could you tell us a little bit more about what data do you, like? How do you calculate that? Because the concept is clear, but how do you?
So now you want me to put up all the mathematics that I skipped, right?
If you want.
No, we don't do this. So we use three data sources. It's the number of cases per day and the number of tests per day. We use the number of new hospitalizations per day. We use the number of imported cases detected at the border every day. These are the data that we use. The model is if you want, it's a very simple and stupid copy of the Norwegian society. It says that you are susceptible, you can get diseased, you can get infected. If you're infected, you can infect others. And we have a computer code that simulates how things can happen. We use, in fact, mobility that is estimated by mobility of the Telenor mobile phones. If you have a Telenor mobile phone, you are in our data. But aggregated, very privacy concerned here, right? So it's the number of people moving from every municipality to each other every 6 hours. But we use this information to understand how people move. Right now, this information is important because the country is empty of a virus. So if people moving out from Oslo, they take the virus with them because Oslo is stronger. During the peaks, it was not important because the virus was everywhere. But these mathematical models are quite well known, and they're not particularly complicated. But they are enough to make predictions. And the R number you're talking about is abstract. It only exists in these models in some sense, right? It's not the temperature, like.
Okay. more questions? Do you have? Yeah. Yeah, you have to turn it on. They will hear you on internet.
Vado più vicino a sentire cosa dice.
Okay.
Sì, sì.
Poi
I'm trying to speak very loudly. So the R number, right? That's kind of the average number that an infected person would infect.
So this is very true, right? So I showed you in the beginning that our current estimate of R is 0.98, but it has a credibility interval between 0.8 and 1.2. This is the uncertainty. And it is still an average in the sense that it's the average number of contacts per person, per infected. Some people are super spreaders. They are those that have lots of contacts and lots of and are dangerous in this situation. And then other people are very boring like me, and I see my wife and my children. And now I see you, right? So it's very, but this is very varying. But it is a completely abstract thing that is not connected to each person. So it's an average. You are completely right, and it's uncertain.
Very practical question. So on the basis of what you said, which practical advice can you give to us? So first of all, take the third vaccine.
Yes.
Is it?
Yes.
Then influenza, the vaccine against influenza, and then avoid big gatherings.
It's difficult. It's a difficult question, right? First, I'm not so, and I'm really not an expert of this. So now I'm a bit like you, right? We guess a bit. But yes, I mean, I think we are well protected today. So I don't think we need an urgent new vaccine. No, we did it maybe around the summer, right? So I think I will start to worry in March, April, not before. Then. With the Pfizer and Moderna. Probably longer. The influenza vaccine, very important to do. You should all do it, even if you're very young and you've never done it in your life. This is the year of doing it, because we didn't have the influenza last year, so we have all lost the immunity. So if we get the influenza this year, it's going to be worse. So it's better to do it. I think that I wonder if I will not travel to London and Moscow. And I think that I think that we will use the facial mask again. Maybe it will not be obligatory. In Italy, everybody uses it, right? In France, everybody uses it. So I think that it will come again in Oslo. Today, I was taking the bus here to come here, and there were 2 or 3 people having it, right? I was surprised. I thought 0. But we are coming back to that, and I don't think the country will do any big interventions. The governments will not lock down things or things. I think more people will work from home. But I think more people will work from home, and this is a big problem for us in the university. We want to have a lively academic environment, and if everybody works at home, we are in trouble.
Okay. Thank you very much. You can proceed now. Welcome back. So, yeah. So now it's time for our second speaker. It's my pleasure to introduce Sabrina Sartori. She's an associate professor at the Department of Technology Systems and their Energy Systems section at the University of Oslo. And she took her PhD in Bologna in material sciences. And then she had a postdoc in Italy, in Padova. And then she moved to Norway in 2006, where she worked as a research scientist at the Institute for Energy Technology. And after that, she was appointed at the University of Oslo in 2013. And now her main research interest is energy storage materials. And in particular, she focuses on synthesis and characterization of materials for hydrogen storage and batteries. So today she's going to talk about sustainable energy for everyone. So this is, again, another very important topic for us. So please, stage is yours.
Thank you very much. It's a pleasure to be here with all of you, and thank you to the Italian Embassy and to the fantastic volunteers that organized this event. Today I'm here to talk about a dream, my personal dream, which is shared with other people's about sustainable energy for everyone, everywhere. And in particular, I will focus on hydrogen storage. We are at a critical time, and my critical time is that the slides are going too fast for me. Why we are at critical time? See, I'm very fast. So you all know about the fossil fuel. We want to go away from fossil fuel, and our renewable energy in the like solar or wind power, they are starting to be, the technology related to renewable energy starts to be very much competitive with the fossil fuel. And there will be a time very soon when these technologies will be really, really competitive. So we need to be ready. However, why am I showing this slide, you think? We have a beautiful art, our beautiful Earth. Any idea? Why am I showing this?
Turn off the light.
Yes, this is night, right? And the other side is day. The problem that we have, which is a challenge, our challenge, is that renewable energy is intermittent. So like day and night. So we have solar energy here. Okay, maybe Norway is not the best for solar energy, but in any case, we have a day, so the sun shines, then we produce electricity with PV, solar photovoltaic, for example. But then what about during the night? What are we going to do? How are we going to use this electricity? Are we going to use electricity during the night? Yes or no? So the challenge is that renewable energy is intermittent. So we need to do something. We need to store the energy that we produce, for example, during the day, the excess electricity that we produce during the day, we need to store it some way or another. We can use batteries. And today I'm going to argue with you that not only batteries, but also hydrogen is important. Yes. Why am I here in Norway? I came here for work, actually, no love. No. Then I stayed here. Also, I found love, but I still argue that I'm here for work, right? So I came here to study hydrogen storage material. Here you see a Mirai, which is produced by Toyota. And they cut it in half just to see how this car is built. Here we have a fuel cell, and here we have a hydrogen storage. So this car is driving power by hydrogen. So I started to do this work working on ways we can store hydrogen for cars. I started to do this in Padova, and then I moved to Oslo, and then many other countries. So I need really to have a bigger sensibility here, because otherwise I'm going to spoil a lot of things because I'm going to, like in school, to ask you questions. And if yes, I will do like that. Yes, I will do like in the old times. So, what is hydrogen? Ta-da! Yes. So, we have 3 isotopes. I'm not going to bother you about this, but hydrogen is a simple element. Then we have a proton and 1 electron. Very good. Then, normally, hydrogen atom likes another hydrogen atom, and they make a molecule. And as a gas, hydrogen is very light, 14 times lighter than air. But it's always bound to other elements. You can never find in nature hydrogen as a gas alone. Yes, you have it, for instance, in water. So H2O, that's just one of the elements. So when we talk about hydrogen cycle, what we talk about? So we need to produce hydrogen through electrolysis. So we split the molecule of water into hydrogen and oxygen. Then oxygen can be released to the atmosphere. Maybe I can use this. And then what we need to do is to try to capture and store this hydrogen. And that's the challenge that I'm going to present today. Why I'm here and why a lot of research is going on around the world on hydrogen storage. Then this hydrogen, once it is captured, can be used in a fuel cell. And in fuel cell, we recombine hydrogen with oxygen, and we can produce electricity to drive our car. So I will start first with transportation. Our old cars driving with the fossil fuel, they are using the fossil fuel, they are running, and unfortunately, they are very inefficient because 70–80% is lost due to heat loss. So it's very inefficient and very expensive. So we don't really like this. Water splitting, what I said before. So if we use renewable, if we use electricity coming from renewable sources like sun or wind, then this electricity splits the molecule of water in oxygen. And here is a bit of chemistry. I hope you bear with me. H2O is water. So hydrogen is produced and also oxygen. And then this hydrogen gas then can be recombined inside a fuel cell. So in the fuel cell, we have the opposite reaction, you see? It goes back. Hydrogen plus oxygen produce water. Actually, you could drink this water coming out from your hydrogen car. You put your tongue under and you can drink it because it's water. And then you can drive your car, and in this case, only 40–50% is lost on heat. So it's a more efficient type of driving your car. However, the difficult step is, the critical step is storage. How am I going to store this hydrogen, which is very volatile? Yes. So why hydrogen? It's 100% renewable. There is no pollution, only water, as we learned, that I can drink. And if we talk about transportation, typically the cars that are being built by Hyundai or Toyota, they can drive up to 400–700 kilometers. It depends on the range. So now I want to just show you some ideas that have been developed along the years. So this is actually the first hydrogen car that was invented in 1807. This was using hydrogen in a combustion engine. Then another French, maybe some French among you, yes, you. He managed to sell 200 of these three-wheels car.
so a little bit rudimental. And then some other modify their car, like this guy here. He modified his Austin, putting on the top tanks containing hydrogen gas. And only in the 60s, General Motors produced the first hydrogen fuel cell car of record, which was able to run for 200 kilometers. So now, like in a high school question. So you have 4 kilograms of hydrogen gas, and you want to put this hydrogen gas in a balloon, and this is the density of hydrogen. How big do you think this balloon will be? Yes, you said
The side of the car.
like a car, the size of the car. Okay, so I will help you with the calculations. I did them for you. So this is the balloon, more or less. So you use the density. You then can calculate the volume, and then you can calculate the radius, and it means that the diameter will be 5.6 meters. And we don't want to go around the city with this kind of balloon, right? No, we don't want. So we need to do something with this hydrogen. What we could do is to compress it, okay? This is one way we can store hydrogen. Our challenge is to store hydrogen in adequate amount of hydrogen in an acceptable volume, pressure, temperature condition. And we want this to be as efficient and cost-effective as possible. And I can tell you this is a really big challenge. For the moment, the car companies are using compressed gas. Typically, cars have tanks which are under 700 bar of hydrogen. If you see hydrogen buses going around the city, sometimes you see them also in Oslo, then these hydrogen buses have a tank which is around 350 bar. You can see them, so you see some hydrogen buses because they have, like on the top, they are like bulky, and that's where the tank are. Another way to store hydrogen is to liquefy it, but then you need to go to such a low temperature, minus 253 degrees C, and means that the tank is very expensive, very complex. BMW proposed something, and as you see, just you don't need to read, but it's the components are very complex. And what I am arguing for you here is that we could use powders, metal powders, inside the tanks. These metal powders of different composition could store hydrogen, could bond with hydrogen in such a way that hydrogen is more compact. The tank will be smaller, and therefore also the tank will occupy less space, and you could have your boyfriend or girlfriend with you in the car and not only the hydrogen tank. Okay, so let's have a look of a comparison. So this is your car, and you want to run 500 kilometers with this car, and then you can choose diesel, compressed natural gas, compressed gas at 700 bar, or lithium batteries. So you can see already from visually that the tanks that you will have different sizes, and actually the battery is very big and heavy, while compressed hydrogen gas will be, the tank will be kind of comparable in size with compressed natural gas, but diesel is still the best. So we have to do a lot of work here to reduce the tank, and with the powders, with these metal powders, actually the tank will be reduced, so smaller in size. But of course, if you want to drive around, then you need also refilling stations. That's a problem, another problem. A standard hydrogen filling station, yes,
cost $4.3 million US, which is 5 times the cost of an ordinary gas station. This means that we need really help from the government if we want to really introduce the hydrogen economy in our society. And this is just an overview of prediction, actually, how we will evolve from, for example, the situation of today. In 5 years, it is predicted that the amount of cars going around our cities fueled by hydrogen will increase dramatically. And here you see some targets. For instance, China has a target of 1 million fuel cell vehicles on the road by 2030. But of course, we need investments for building filling stations. So again, another way to see the car. Then we have the fuel cell and the tank and some battery packs, and then the electrical engine here. As you all know, the car with battery vehicle are very popular, especially in Norway. And we say that probably electric vehicle will be successful in cities. For a longer range, hydrogen is still a very good solution, but hydrogen is very, very good solution for heavy transportation, like trucks. This is a truck built by Toyota. And here the fuel cell and the hydrogen tank are at the front. Also in Norway, a lot of money are put on new ferries and boats, which will adopt hydrogen. For instance, there is the plans to at least have some of this Hurtigruten going from Bergen to Kirkenes, and some of them should drive with the hydrogen, and they should be, at least some of them, in operation by 2022. In Germany, there is already on the road, on the rail, train driven by hydrogen, and again, the fuel cell and hydrogen is here on the top. This is Germany, and it takes only 15 minutes to refuel, so you don't need to wait hours to refuel your train with hydrogen. Also, another example is in UK, and I think in Norway they are also planning to have a hydrogen power train. So I've been talking about transportation, but since I think 5 years now, I'm starting to be very interested in using hydrogen also for stationary application. Really, when we want to increase the amount of renewable energy in our grid, this problem of intermittence starts to be very urgent, because intermittency means that you have instability and fluctuations of electricity supply. Like you come home and you don't have electricity because suddenly there is no wind or there is no sun. So it's important to also store hydrogen for stationary applications. And the grid of the future will be completely different from the grid of today. Today, basically, the grid, how it is working. The grid provides electricity based on your needs. But in the future, with hydrogen storage or with electricity storage, we will be able to store this electricity and use it later on when we need. So we break this need of immediate reaction to the availability of the demand. So electrification, decentralization, and digitalization will be important for this transformation. What is also very nice is that once you have hydrogen storage or batteries, you can use this storage in different points of the grid. and therefore you can diversify also the way you can store energy. I'm maybe going more technical now. Yes, if we compare the capacity, so how much power per time, so from minutes to season. Typically, batteries are used for storage that lasts 1-2 days. But let's say that you have an excess of wind, a lot of wind during summer, and that you want to use this excess in 6 months' time. So you cannot use batteries because batteries discharge, you know, as well with your phone. You need to charge because even if you don't use your phone, it discharges by itself. That's a problem. So if you use hydrogen, hydrogen has this big, larger flexibility, so you can use it after months. It's still there, it's still stored. That's an important advantage. So I will go on quickly here. Some examples. This is a building in Brisbane, in Australia, which is completely covered by a solar panel, and then they store the excess electricity with the hydrogen storage. Hydrogen storage is something I'm doing also in the lab and around the world. We measure, so we synthesize the material and then we go around the world to characterize the material. Several types of stationary applications are already starting to see the light in Japan, for example, in containers where they have this hydrogen plus fuel cell. That's something we are also going to develop, and I'm going to jump very quickly to some of the projects that we are having in our team. So one PhD is, for example, studying some type of composition for metal hydrides to store excess electricity from wind and sun in a Norwegian grid. With another PhD, we are actually developing hydrogen storage for a floating wind turbine. And the idea here is that the boat will dock to the floating wind turbine and will charge the boats with hydrogen. Another fantastic project is this new telescope, which with this European project we are designing for the Atacama Desert, and my team is charged to design this telescope for the first time as a renewable, as a sustainable telescope, completely powered by renewable energy and hydrogen. This will be done in Chile, hopefully. This is a design project, so I hope that we will be able to build it in a few years' time. What about hydrogen and aviation? We don't know, but there are some ideas there, some startup that propose this kind of airplane, where when the airplane lands, then you exchange this nacelle, which are containing hydrogen obtained by renewable energy. So with this, I hope I convinced you that hydrogen could be a good alternative to give us sustainable energy for everyone, everywhere. Thank you so much.
Yes. Thank you. Thank you very much. It was really interesting. Do we have any questions? Okay, start there. So how do I use it? No, it's on. Just keep it like. Can you hear me? Yeah, that's fine. Wonderful lecture. I learned a lot. But I do wonder about one thing. It seems dangerous with the hydrogen tanks. Is there a risk if you're riding a bus with the tanks on or cars? Like, is it? What happens if you crash?
Yeah, so these tanks are very, very stable. They, of course, there are crash tests, like with all tanks. So they are not going to break. Don't worry. But in any case, the reason why they are on the top is because in any case the hydrogen flames goes up. So then, in case of really unlike event that something breaks, anyway, the flame will go up. So there will be no explosion on the bus itself. But these powders, for instance, they are very they are working at low pressure and temperature. We play around, so there is 100 or I cannot never say 100% safety, but they are much safer than any other hydrogen technology. Thank you.
Hi. I was wondering if this metal powder that you need to use, if you can reuse it over and over, or if you have to worry about how to dispose it at some point.
Yeah, they are very, so of course we do a lot of research to make this powder recyclable. So the ones that we are using are chosen because the type of materials, first of all, we choose the materials that are most sustainable, like this iron, titanium, for example. And then the cyclability, so you can make cycles that are completely reversible. That's the aim. Yeah.
Because otherwise,
absolutely. No, yeah, absolutely. So we take care of that by designing the right composition. Yeah. Thank you.
I know that some countries like Australia already started thinking about hydrogen storage in large scale, like storing excess electricity for bad times or when it's more suitable for the grid. Are we starting to think about that in Norway too? If so, what is the strategy?
Yeah, thank you. I would really love that the strategy is similar to the one in Australia. As you may heard that the Norwegian government last year actually released the hydrogen strategy. They are putting a lot of money on hydrogen. Now they open a new SFF, both SFF and FME on hydrogen. So there is a strategy there to increase the amount of money, both on transportation, but I would say on stationary application, because Norway is very strong technologically, so we shouldn't lose that edge that we have. We are very well positioned internationally. So the strategy here from the Norwegian government is also to support these activities, and the companies are also on board, like Equinor and other big companies that wants to sell themselves also as more renewable, from a more renewable aspect. So good strategy there as well. At least I want to see. I mean, I will see next year when the money will be given, really. For the moment, they announced, and there is a call actually in November. We need to submit a big application. Thank you.
A wonderful future, you tell us. But I was wondering, not all the buses in Oslo has hydrogen. So what is the challenge? Why is it not the full story already? What is the bottleneck still?
Yeah, there are Router is studying now with us actually the development of a big fleet, a large fleet of buses on hydrogen. So we are studying with them which type. The refilling, the fuel station, the refilling station are very expensive. So you need to have support to be able to build them. As you saw, when the cost is so high, I mean, a router alone cannot do it. Then there are other technologies, also biofuel, for instance, is very much used. I would say that we should think differently now compared to the past, where only fossil fuel was used. We have a wonderful type of technologies, so several type of technologies that we can use at the same time. So I don't see these big competitions. But the more buses we have, the more incentives we have to build filling stations. So, and then people are waiting, and yeah, so, but I would say costs are the major bottleneck because the technology is there now, at least for compressed hydrogen. Yeah.
Any more questions? Okay.
Thank you.
Third speaker, who is Luca Menegon. And Luca is a professor of geology at the NUWD, yeah?
Yeah, the New Center.
Center, and the Department of Geoscience in University of Oslo. You are from Padua, or you studied?
Kind of. I'm from Bolzano, but I spent most of my Italian life in Padua. Yes.
Okay. Yeah, and you graduated at the University of Padua, and you also did your PhD there. And then you moved to Stockholm and to Tromsø for postdoc. And then you were a lecturer in the University of Plymouth in the UK. So then in 2019, you moved back to Norway, to Oslo. And you started your you're a researcher, so you study earthquake geology, which is really interesting, and rock deformation, and you combine geological field work with experiments and with material characterization with electron microscopy. So very wide,
broad,
from
yes,
little to
yes.
wide. Okay, so tonight you're gonna speak to us about hunting for fossil earthquakes in Norway. So,
cheers.
Please, stage is yours.
Thank you. Okay. So thank you very much, Pint of Science, for providing this wonderful service to the scientific community, and also for fostering really outreach and dissemination. We all need each other, so thank you very much for your effort. Okay, so how did I end up in Norway? That's a long story. So I started, for the first time I came to Norway in 2001, and as a young Erasmus student to Tromsø. I thought I kind of like it. So it's quite nice, you know, outdoor activity, beautiful Arctic sceneries, all these things. But then I had to go back to Italy to finish my degree. And then in 2009, I had an offer for a postdoc, again to Tromsø. I went back to Tromsø. But then, you know, postdoc, 3 years, I had to leave, right? So I left and I drifted towards the UK. I went to the UK, which was a lovely experience. 7 wonderful years in Plymouth. And then I had this opportunity to come back to Oslo. So the bottom line is that I'm very slow learning. So it took me about 20 years to learn that I really like Norway. So we came back here in 2019, and it's about time to learn Norwegian now for me after 3 attempts. So I'll do my best to do that. I also came back to Norway for love, but for love for rocks predominantly. So my wife is Italian, and she has always followed me in this journey, in this exciting journey. All right. Okay. I'm trying to convince you that Norway is a great place to study earthquakes, although it's not particularly affected by earthquake hazards. We can come back to this in a minute, but it's a great place to learn more about earthquakes, especially by looking at rocks. What can a rock tell us about earthquakes? So today, in the next 30 minutes, I'm trying to convince you that we can put our fingers on a fossil earthquakes and touch what happens to rocks during an earthquake. And I also would like to convince you that although perhaps the elevation is not exactly the same, but we do have the Himalayas in Norway. And then I would also like to convince you that every earthquake starts really with the size of a single grain. Okay, what are earthquakes? Earthquakes are probably, together with volcanoes and volcanic activities, are probably the most spectacular
manifestation of plate tectonics, so the processes that shape the Earth surface, but also they are driven by the Earth interiors, right? So earthquakes are caused because tectonic plates move. They like to move. They are not really lazy. They inevitably move, and they touch each other along what we call plate boundaries and faults. And faults are deformation zones and fracture zones in the Earth crust. And at some point, the friction really becomes a problem. Frictional resistance between them, and the rocks cannot really continue to move and to creep. And when the friction is too high, and when the rocks overcome this frictional resistance, an earthquake happens. This is a nice yes. Sorry, I'm not multitasking, and that's a brutal reality. I'm not multitasking. So I'll try to go back to this, yes, and I'll show you this animation, hopefully. Yes, there we go. It shows you what happens when two plates, tectonic plates, move past each other. And there is some, what we geologists call an asperity. So it's a place where friction localizes, and it becomes an impediment for further movement. Rocks fail and generate an earthquakes due to the stress and to the energy released in friction. This is the San Andreas fault in California, which is, again, a particularly spectacular example of what happens when two plates move next to each other. And needless to say, the San Andreas fault is quite famous for hosting large quakes. Okay, where do earthquakes happen on Earth? They're pretty much everywhere. That's the sad news. The good news is that if we don't live particularly close to plate boundaries, which are exactly the areas on the Earth's surfaces where two plates are next to each other, earthquakes are less frequent than otherwise. So this is a plot of the density of earthquakes and volcanic eruptions on Earth. And you can see that they're not really randomly distributed, they're not really scattered. They do follow certain patterns. For example, here you can, perhaps those of you who are more familiar, I know that there are quite a lot of geoscientists in the room. I feel very under pressure here, but I'll try to do my best to be rigorous. These are lineaments that define what we call the mid-ocean ridge, so a divergent plate boundary. And earthquakes and volcanoes, they do follow these trends, right? So where plates move either towards each other or away from each other or past each other, we have more geological activity. That's where the action takes place. Likewise, here is when the Andes mountain belt forms. That's the Pacific plate is moving underneath the South American plate here. So we have a bunch of earthquakes and volcanoes occurring up there. As a consequence of this distribution of earthquakes and volcanoes, the seismic hazard really is mirroring this pattern. And from white to red, we have a pattern from low seismic hazard to high seismic hazard. High seismic hazard tends to be localized where plate boundaries are, especially in the continents. This map refers exclusively to the continents. Yeah, so we are relatively safe up here in Norway. A bit less so in Italy, and a bit less so in other places like the Himalaya or Japan. So although earthquakes predominantly occur at plate boundaries, also plate interior, so what we call the interior of tectonic plates, what is, within the plates, something like here or like here, away from plate boundaries, they're also affected quite heavily in place by earthquake activity. Okay, let's zoom in Europe, right? So this is an earthquake hazard map of Europe. Again, warm colors define very high, high to very high earthquake hazard, and green to white is a fairly low earthquake hazard. So not surprisingly, where we identify what we call plate boundaries, as I said, we have very high earthquake hazard. This is a fault that is known as the North Anatolian fault. So Istanbul is probably one of the most dangerous cities to live at the moment. The North Anatolian fault, this fault here, is particularly prone or keen to nucleate earthquakes. And the sad news is that historically, the earthquakes, the seismicity is migrating from east to west. And the last big quakes, the 1999 Izmit quake, nucleated somewhere here. So the progressive westward migration of earthquakes is likely to hit Istanbul pretty soon, at least from a historical seismological viewpoint. So Istanbul is quite affected by earthquake hazard. Okay, so Italy is fairly affected as well. That's why I escaped from Italy. I migrated to Norway, which is, as I say, relatively unaffected. I also experienced UK, and I deliberately decided to move to the really lowermost risk area, which is Plymouth. It's down here. There's nothing happening tectonically down there. It's quite boring compared to Wales and other parts of the country. But then I thought, well, I didn't really understand very well the earthquake risk in Norway, so I have to go back and see what happens up there. But yet, certainly these two places, both of them are fairly safe compared to the Mediterranean area, which is due to the fact that Africa is pushing quite hard towards Europe, and therefore all these fractures and deformation zones in the lithosphere are quite prone to localize and nucleate earthquakes in this domain here of Southern Europe, as you can see from the warm colors. What about Norway? Well, Norway is fairly safe, as I said. It's not unaffected by earthquake activities. This is the map of earthquake distribution, I think in 2000 to 2001, published by NORSAR, that is the seismological or is the Norwegian seismic arrays. So there is not much, there are many earthquakes happening here. The vast majority of earthquakes in the northern part of Scandinavia are happening in this part of the world here, not too far from Spitsbergen. That's because this is a divergent plate boundary. So this plate is moving away from this plate, and this movement is accommodated by fracturing along this trend here. So there is intense fracturing here that nucleates earthquakes. But in continental Norway, there aren't many earthquakes historically. Probably the last important earthquakes recorded in Norway was in 23rd of October 1904 here in Oslo. It was a magnitude 5.4, so quite substantial. It destroyed one church, and it didn't cause too many injuries among the population, luckily. But that's one of it is the last really historical important earthquakes in the area. Earthquakes are fairly shallow geological processes, really. By shallow, I mean things that happen, that nucleates within the first 50 kilometers of depth in the crust and in the lithosphere. We have a map here that is color-coded according to depth, the depth of the nucleation of earthquakes. In red, you have 0 to 20 kilometers, and then you progress towards deeper earthquakes nucleation depth, down to 700 kilometers that are particularly enigmatic to understand, and they are typically related to what we call subduction zone, where one tectonic plate is really sinking underneath another tectonic plate. So they're predominantly shallow phenomena that happens within the first, let's say, 50 kilometers of depth. But within these 50 kilometers of depth, we can identify also a further division or further category of earthquakes. So most of the earthquakes within this 50 kilometers depth, they occur within the first 15 to 20. The reason for that is because at this depth, 15 kilometers, the earth, the rocks are really cold and brittle. They're like glass. When you hammer glass, it is, you destroy it, right? It's brittle, it cracks. They are not capable of flowing. Below this depth, the rocks would flow. If they are subjected to tectonic forces, they would flow like a chewing gum, and earthquakes would not happen down there. Okay, so bear in mind, About 15 to 20 kilometers is really the lowermost depth of what we call the seismogenic zone. So below this depth, we should not really expect earthquakes in the crust. What about the energy released by earthquakes? That's quite an interesting topic to discuss. This is a diagram that shows you a bunch of data and numbers and different energies released by earthquakes. What we will refer to is what we call the magnitude. The magnitude is the intensity, the size of an earthquake. It tells you how much energy has been released. So here you see on the left-hand side, on the y-axis, you see the magnitude of earthquakes that increase from 2 to 10. So 10 is something that we don't want to experience. 2 is something that we probably experience every day without really noticing that. And here you see that this diagram, this sort of pyramid is, of course, becoming more pointy towards the high magnitude. And that's because this diagram gives you the distribution, the frequency of different earthquakes of different magnitudes. So there is a bunch, there are many earthquakes of low magnitudes happening every year. About 1 million of earthquakes of magnitude 2 per year globally, statistically. And luckily, thankfully, less than 1 of magnitude 10 or 9.5 per year in the world. Then this means that tectonics, nature has devised a way of dissipating energy, not necessarily in a catastrophic way, although catastrophes are a very good word to get people interested in geology, but nature is quite able to dissipate energy without necessarily going into catastrophe. So they dissipate energy with low magnitude earthquakes as well. On the right-hand side here, you see analogs or things that we can use to understand the extent of energy released during specific earthquakes or earthquakes of specific magnitudes. For example, an earthquake of magnitude 3 corresponds roughly to the energy released of a large lightning bolt. The Mount St. Helens eruption that many of you perhaps are familiar with because you read about it in 1980, I think it was, released an energy comparable to an earthquake of magnitude 8, which is quite substantial. In terms of earthquakes that you may have heard of, Sumatra, the 2004 Sumatra was a 9.1, so I said wine because I always think of wine, but I wanted to say 9.1. Apologize for that. 9.1 was particularly high earthquakes, particularly strong earthquake. Tohoku, similarly. The largest earthquake ever recorded is the one in Valdivia in Chile in 1960, 9.4. Luckily, it happened in a place in the world that was largely inhabited. So it was the amount of people around there was not particularly high. So it is still intensely studied as the strongest earthquakes recorded on Earth, but luckily not many damages were induced. So this is a quotation from a paper that described what happened during the Tohoku earthquake in 2011 in Japan, and also compared a little bit the energy released with something that we may have a bit more of a feeling for, which are explosions, right? So the earthquake in Tohoku, first of all, lasted for quite a while and lifted the seafloor by as much as 5 meters over 15,000 square kilometers. And the displacement was as large as 60 to 80 meters. And the total energy released was equivalent to 100 megaton explosion. So we're talking about really spectacular geological phenomena. Okay, energy of earthquakes. What is the energy of earthquakes? So we know that an earthquake occurs and ground is shaking, but what is the energy of an earthquake? So the energy of an earthquake is probably one of the most intensely debated issues in the geosciences. And although we feel that the ground shaking is the most tremendous manifestation of energy, we have to say that the ground shaking, what we call the radiated energy, the energy that is dissipated in the form of seismic waves, is really a tiny fraction of the energy of an earthquake. Is normally less than 20%. In this pie chart, we have one estimate. So it's normally less than 20%. The other two fundamental components of the energy released during an earthquake is actually fracture energy, so the energy that nature uses to crack rocks, to destroy rocks, to fracture rocks during the propagation of an earthquake. But the vast majority of it is actually heat, is friction. So if you slide your hands slow or fast, you will generate heat. Yeah. So luckily you don't generate an earthquake, but you generate heat. Yeah. So you can understand what friction causes, right? So the frictional heat released during earthquakes is really the highest component of the energy released during an earthquake. Where does this heat go? Is it heating our houses or what? No, unfortunately it doesn't. So this heat normally goes into melting the rocks. And this is a special type of rocks that many of us study and are quite engaged with. They're called pseudotachelites, this terribly difficult name that's really not making our life easy at all. But pseudotachelites are really spectacular rocks because they are fossil earthquakes. So these are rocks that form when the rocks melt due to friction. And I report here the first description of pseudotachelites that happened about 1 century ago, if I remember correctly. Yes, and an inclusion-rich black rock with a glassy cryptocrystalline matrix, blah, 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 right? Okay, so why did I show meteorite here, an impact here? It's because pseudotachelites, which are this type of rocks here, these black rocks with the fragments and clast here, they tend to form during impact by meteorites as well, because the shock deformation caused by the impact by a big body at the supersonic velocities destroys, pulverizes, and melt the rocks. These are what we call the impact-generated pseudotachelites. So the first time that pseudotachelites were discovered, really, and I'm referring to this paper in 1916, they were discovered in South Africa. These are really spectacular, really cliffs of these black pseudotachelites forming these fields of black rocks around these fragments of what we call the host rock, the rock that has been blasted really during the impact of the meteorite. So at that time, it was believed that only meteorite impact or impacts could develop pseudotachelites, but it has become progressively clearer and more evident, and also tectonics can form pseudotachelites. Also, earthquakes can form pseudotachelites. This is an example of a black rock that we call pseudotachelites with this flame-shaped structure that we call injection veins. That's where the melt that form during frictional heat during an earthquake injects into the host rock. This is a granite. The photo is taken from a very famous fault in the Italian Alps that became one of the most outstanding natural laboratories to study fossil earthquakes in the world. So if you put your finger here, you're touching a fossil earthquake. Yeah. What can we do to understand better how these fossil earthquakes, how these pseudotachelites forms? Well, we can perform experiments, and this is what the National Institute of Geophysics and Volcanology in Italy is doing at the moment, using the Shiva apparatus, slow to high velocity apparatus that is probably the most important earthquake simulator in the world. I'll try to show you a video clip now. Interesting. Doesn't, yeah. I'll click on this. Surprise. Let's see if it works. It does. Probably. There we go. Okay. So this is an experiment, right? Where the scientists have well, I don't see this on screen. I'll try to navigate you through it. So so there are two cylinders of rocks here sliding past each other at seismic velocities, yeah, at more than 1 meter per second. So what happens is that they melt. Okay, so the friction released during this high velocity slip event causes melting of rocks. Now the big question is, how can I go back to the presentation for a non-multitasking person like me? I'm back there, yes, but not there. Super. Thank you. Okay. Thanks a lot. Okay, so these rocks form because of the tremendous frictional heat released during a earthquake slip. Okay, Norway now. Norway hosts probably among the most spectacular example of pseudotachylites in the world, of tectonic pseudotachylites in the world. More specifically in Lofoten and in what we geologists call the westernized region of the Bergen Arcs, or in a more simple way, Bergen. Okay, so rocks are, the pseudotachylites, they look like this in the field. They have this darker appearance compared to the host rock. This layer here is what we call the generation surface. That's where the two fault blocks have slipped during the earthquake. And this flame-shaped structure is what we call the injection vein. That's where the melt decided to escape from the slip surface and wanted to inject the host rock. Regardless of these details, I mean, these rocks here are really incredibly valuable natural laboratories for geologists, because we can really take a sample and study, their properties, their characteristics, and help seismologists to understand what happens when earthquakes occur. On top of that, we have to say also that the earthquakes in Norway, the pseudotachylites in Norway, are special. They're not really easy ones. They are quite special because although, as I said earlier, the typical seismogenic layer in the crust is, let's say, 15 to 20 kilometers deep maximum, the earthquakes in Norway, they want to make our life difficult, which is fine, take the challenge. They typically form at pressures or depth in excess of 20 kilometers, so deeper than that, where they shouldn't form. Simply, they shouldn't be there. So why are they there? So although most of the earthquakes happen between 10 and 15 kilometers, the pseudotachylites in Norway, they form down here. So they are representative of a category of earthquakes that is really poorly known, which make them even more valuable, because we can really touch something that is so enigmatic and really deserves of more research. Why are they not supposed to be there? Because at those depths, at 25, 30, 40 kilometers, the rocks should be so weak, they should be flowing like butter, yeah? Like this rock shows you, it should, this flow structures, this fold, this, evidence of flowing of rocks. Because when you heat rocks very much, and when you compress them very much, they are not happy to fracture. They don't want to fracture. They respond to tectonic forces by flowing slowly, like a chewing gum. And it's really, the interesting thing is really all down to water. So the fact that these rocks at depth are capable of flowing is because they contain tiny little amount of water in the crystal lattice. The minerals, quartz or plagioclase, for those of you who knows minerals, they contain a little bit of water in the crystal lattice. And this water sort of lubricates the lattice and makes it possible for the lattice to flow, to creep. This is an example of these tiny little molecules of water, what we call fluid inclusions. They are less than half a micron in size, that are found within the crystals. If there is no such water, the crystals, they don't flow. They are lazy. They just build up all the tectonic forces and they crack. There are lower crustal earthquakes recorded present day in the world. India, under thrusting Asia, so in Tibet, is the most obvious example. So you see here, all these dots are earthquakes, and they are color-coded according to depth. So there are earthquakes that are fairly deep here. And we think that the fact that India has these deep earthquakes depend on the fact that the Indian rocks are really, really dry. They don't have any water in the crystal lattice, which means that we can probably use the occurrence, the distribution of lower crustal earthquakes as a proxy really for the amount of water that is found in the continental crust. That's quite interesting. Lower crustal earthquakes are not really just academic curiosity at all. They do happen, as I showed in the previous slide about India. In 1966, there was magnitude 7 almost earthquakes at depth of 25 kilometers in Pakistan. A couple of weeks ago, there was one of magnitudes about 4 in Iran. 1 week ago, there was a magnitude 4.5 or 4, I don't remember, still in Iran. So there are lower crustal earthquakes. They are typically within the continents, and they are typically part of the earthquake deformation cycle that can really affect quite a lot society and infrastructure quite heavily. But even much closer to us, because the 1904 Oslo earthquake of magnitude 5.4, which is quite substantial. If there is a 5.4 now, probably we won't be able to enjoy our beers very much in this moment. So it will be something quite substantial. So maybe something more shaky than a beer, yeah? So the 1904 earthquake was a lower crustal earthquake, was nucleated at 25 to 30 kilometers here in Oslo. That means that we really need to understand better how they work. Yeah, we really need to understand better how it is possible to have earthquakes at those depths, which is one of the fundamental, really, research lines of our research group at New York at the University of Oslo. And yes, these earthquakes in the lower crust of the Himalaya are probably the most obvious present-day example of lower crustal earthquakes. And as I say, the Norwegian rocks are really an analog for this type of processes. So I like to think that we do have the Himalayas in our backyard. So here we are looking at fossil earthquakes in Holsnøy, which is an island not too far from Bergen in 2019. So we can think of our Mount Everest or K2 not too far from there. Likewise, Lofoten is a fantastic natural laboratory to look at lower crustal earthquakes, because these rocks that we are quite happily investigating for your master, PhD, postdoc, and research projects, they contain evidence of earthquakes that nucleated at pressure and depth deeper than 20 to 25, 30, 40 kilometers as well. So this actually is quite fantastic in my view, because it gives us the direct observation to processes that are really inaccessible to our everyday life, right? We're looking at how the Earth behaves at 25, 30, 40 kilometers deep, which is something that the most advanced technological projects are never able to achieve. This is the deepest hole that we dug on Earth in the Kola Peninsula. It reached about 12 kilometers, if I remember correctly, at 12.2 kilometers deep. It has been more or less safely covered. Yeah, the diameter is probably less than 5 centimeters. So it's really a very, very small, detailed record of what happens down there. Really, it has scratched the surface of the Earth. It has been tickling the Earth crust, really. So we do need to rely on chunks of the Earth crust that have been brought up to the surface thanks to tectonic processes and mechanisms for us to directly observe how the Earth behaves at depth. How do we do that? So in addition to spend a good time in the field in Lofoten and Holsnøy where it doesn't rain, it can be miserable. But when it doesn't rain, it's really lovely. So we take measurements of the structures, and from measurements we can estimate the magnitude of earthquakes, from measurements of the thickness of the fault, of the offset, so how much the fault has moved. But we also take samples because we really need to dive into the secrets of the single grain processes down there. So we dive into the secrets of single grains by means of what we call electron microscopy, and or just microscopy, and we look at what the microstructure of the rocks look like. So from different type of features like boundaries of grains, like shape of grains, like grain sizes. We can derive properties like the amount of deformation, the amount of strain, how much the crystal lattice has been distorted, how much stress, how much energy has been imposed to the grains, how much heat has been imposed to the grains, what were the temperature and pressure conditions under which the deformation event, the earthquake, took place. And we rely, as I said, on tools that are quite advanced, like the electron microscope that we have at the University of Oslo. Putting together this field observation with this, what we call the thin section. So we cut rock slices quite thin, 30 micrometers, so that the light can go through it and we can look at them with a microscope. We were able to derive models for the generation of these enigmatic deep crustal earthquakes. And there are plenty of these models, all of them more or less valid, or all of them need to be investigated further to be legitimated more and more. This one has been put forward by our group in the University of Oslo. It is a model by which earthquakes that originate in the upper part of the crust, where they are supposed to originate, 15 kilometers, they generate so much energy, so much stress in the crust, that this stress can propagate downwards to infiltrate down the deepest portion of the crust and also induce fracturing and earthquakes there where they should not really happen. So this is a research direction that has blossomed in Oslo, really. That's we really find this research line particularly, how can I say, it's a jewel of UIO, really. It's something that UIO has been putting or pushing for in the last 20, 30 years. So the study of deep earthquakes is something that Oslo really excels for and is worldwide recognized for. Mostly thanks to the Norwegian rocks that are really superb. Okay, then I leave you with this last slide, which is just an advert, really, of a movie, of a documentary that has been produced in 2017 by a Norwegian filmmaker from the University of Plymouth, Heidi Morstein, who is very much interested in describing how scientific research is conducted, how teamwork works, and how, in this case, field work works. So Heidi is a great filmmaker, is a great person that contributes to outreach and dissemination in science. This is her Vimeo website where you can find different clips and movies about either the movie pseudotachylides that I am referring to or other things that she has been producing in the past. Then again, my terrible non-multitasking approach.
It works.
It works now.
No, not yet.
Yeah, I told you. See? Yeah. You put together a French and an Italian, this is the result. Yeah, okay, perfect. And okay, just to conclude, this is just to show. No, there was another one before.
I came back.
You came back. Okay, that's Heidi and Patrick, the filmmaker and the cameraman in Lofoten in the summer of 2017, when they followed us to film us during our field work when we were collecting data to understand these enigmatic lower crustal earthquakes. So at the end of this week, where they followed us, all the geologists wanted to become filmmakers, and the filmmakers wanted to become geologists. So I think this is a very successful experience and experiment, and I hope more of them can follow soon. And that's all. Thank you. It's a pint of science, after all. Yes.
Thank you very much, Luca. Questions? One there.
So
Yes.
it's a more a curiosity. So I was observing in Chile a few years ago, and we experienced the 8 point something earthquake. And it felt very different from the Italian earthquakes, which I experienced before. So the Assisi one, the L'Aquila one, and the Amatrice one. So is this so the Chilean one was very like wavy. It was like being on a boat, whereas the Italian ones are very shaky. And the Chilean one, then it never stopped, but it was not aggressive in the sense that you felt like you were drunk on a boat. So is this because of the depth, or is something completely different?
There are many factors that concur to the way how earthquakes are felt. One is the depth, as you mentioned, but one is also the characteristic of the bedrock. If the bedrock is stiffer, or if the bedrock is softer, or even loose, like loose sediments, like like sands or clays, then the fracture can propagate the waves, can propagate in such a way that you feel like liquefaction and a lot of shaking. So it depends. It depends on the characteristic of the bedrock and on the depth. So yeah, earthquakes of the same magnitude can really be felt in a tremendously different way by different communities.
And also the Chilean ones are waiting for the big one. They always say like, for the past 10 years, they say they're waiting for the magnitude 10 one. And they say, well,
I already got a 9.5. I'd be happy with that. So not necessarily invoking a magnitude 10. So, yeah.
When you study your the difficult word,
yes,
the fossils,
pseudotachylides,
are you able to estimate when these fossils were formed?
Wow, that's a difficult question. We hope we are able to. Well, in some cases, yes, we do, because we can rely on what we call geochronology, so we can measure the age of rocks. By looking at radioactive decay of specific minerals that lend themselves to be dated in this way. But it's not necessarily the case that pseudotachylides are suitable for this purpose. So it can happen, if we are lucky, that we can date them directly. So we can say this earthquake is 25 million years old. In other cases, we have to speculate the age or derive the age from other geological observation, like structures that cut each other. So if the pseudotachylides is cut by something else of which we can measure the age, then we know the minimum age of the earthquake, if that makes sense. Otherwise, we get a drink and I'll explain you better later. Yeah.
Follow-up question still about age. These fossils create themselves very deep in the earth. How long does it take for them to emerge, for you to find them?
I'm sweating now. I use the very, how can I say, general answer. It depends. It depends. Truly, it depends. So normally it is due to the tectonic processes, the tectonic forces that result in uplift and exhumation of rocks. It can, we have pseudotachylides that formed 2 billion of years ago, now exposed at the surface, as well as pseudotachylides that are as young as 20 million years ago or younger. Safe.
I have a related question. How do you, apparently not loud enough. So how do you estimate the depth of the faulting? So 20, 30 kilometers versus 40 kilometers, like if it's 2 million years or 2 billion years, how do you estimate?
We look at the minerals that we find into these fault rocks, in the pseudotachylides. Minerals are stable at different pressure and temperature conditions in the Earth. We know that from thermodynamic modeling of mineral equilibria, and we know that also from experimental, what we call experimental petrology. So we deform and form minerals at different pressure and temperature with what we call pressure vessels. So big experimental devices that allow us to reach in very limited volumes temperature and pressure that are comparable to what is encountered down at 20, 30, 40, 50 kilometers deep. And by comparison between experiments and nature, we infer that the minerals that we see in nature form at certain depth and temperature conditions. So it's an indirect approach. So unfortunately, we cannot put our finger on the rock and say, well, 20 kilometers. No, we need to make observations, measure mineral composition, mineral chemistry, and compare with the models and experiments.
Presentation. I also have a calculation question, and it's about your diagram about how much goes to ripple and how much goes to crushing of the rocks and how much goes to the friction. I understand how you can measure the heat that goes in and change the crystal structure of the pseudotactylite, but how do you establish the difference between what goes into the friction, what goes into the heat, and what goes into the ripple?
That's a fundamental question in seismology, in earthquake geology. So the earthquake energy balance is heavily debated, really. At the moment, the most traditional tool is seismology. So it's the amplitude of seismic waves, and is an indirect observation, right? We are trying to contribute more and more with field geology, with experiments, by measuring, for example, the density of fractures in rocks that have been affected by earthquakes with pseudotachylites. And we try to understand how much energy goes into fracturing the rock, into cracking the rocks. It's mostly a combination between seismological observations, so indirect observation of seismic waves, and geological observations, so direct observations of geological records of rocks. But the numbers are, fluctuate quite a lot. But the thing that we are fairly, confident with is that the radiated energy is a small fraction of the energy budget, up to 20%. All the rest goes somewhere else, thankfully.
Now that we all learned that word of pseudotachylas, right? Is it like this, that every time I see a gray rock with a black line, it's that or not?
I wish it was the case, but no. But unfortunately, we need to go to the field together, and pseudotachylite means that the rock is almost like a tachylite, right? A tachylite is a volcanic glass. It's basically a basalt. Because the two rocks share many similarities. There are certain subtle things that make them different. You normally need a microscope to identify these differences. There are certain things that may be picked also in the field, but are not necessarily easy to get quickly. But yes, maybe we can have a field trip in the Oslo fjord to hunt for them at some point together. Good idea, right? Yeah. All right.
Okay. We'll proceed. Thank you very much.
To join.
Wait. I'm not ready. I'm shooting.
And also people streaming.
Yes, please, people from the streaming, you can also participate. You're more than welcome.
But there's a 10-second delay, so I can try.
Your microphone from the streaming is on or off, or it's on?
Wait, I can check.
I was covering it.
I'm multitasking.
That's fine. Actually, we got better. That is way better.
Which one?
Yeah, just let's switch. Yeah, it's way better than that. So
Okay. Okay. There you go. Should I? Okay, so
I'm coming.
we're waiting just a couple of more seconds for more people to join. So the code up there in the screen, in case you guys haven't seen it, you can join. Okay, while more people is joining, I'm just gonna say that there's a prize for the winner. So thank you so much for sticking around. I think the prize is gonna be one of our super cool T-shirts that you can see here. So just something to keep in mind. Faster you reply, the more points you will get. So keep that in mind, please. And I think now we're ready to go. Yes? Okay. So let's start with the first question. There. So, can earthquakes be predicted? Yes, no, or sometimes? Oh, interesting. So basically, no, not really. They cannot really be predicted. They can be estimated, or we can estimate the probability of them happening. There you go. So, who do you have in the lead? We have Tore. Yes, Tore and San Elmo. Very well done.
Geologist, no?
Next question. Okay, so what is a pandemic? Any disease, same as an outbreak, or it's a global spread of a disease? And the answer is yes, the global spread of a disease. So, very well. Well, actually, COVID, as you guys know, it was not the very first pandemic happening. There has been other diseases such as the Spanish influenza or even the Black Death happening around. And, well, there hasn't been much changes, but there's a lot of questions still to go. So let's see. Next question. So, what can be related to the world sustainable? Ecological balance, social problems, or over-exploitation? Yes, ecological balance. So usually when we're talking about sustainable or something being sustainable, we're referring to activities or products that kind of have a certain improvement in the consumption of natural resources. So let's continue. See, things can change. So now San Elmo is on the lead. Okay, 4th question. Where do earthquakes occur? So everywhere, or mainly in tropical regions, or just where volcanoes are? So yes, everywhere, all around the world. So as you guys already heard, they mainly occur close to the active fault. For example, in the Ring of Fire, that's one of the most active areas in the world. Okay, congratulations to San Elmo. It's still on the lead. There you go. Next question. So, when was COVID declared a pandemic? At the beginning of 2020, in March of 2020, or was it only until July 2020? Nice. Yes, it was, if I'm not mistaken, actually on the 11th of March of 2020 that WHO declared COVID a pandemic. So, oh, there's a new name, Beyond. Nice. Yes. Oh, yes. Things got Pingu. Nice. Okay. Question 6. So, what's an example of energy storage? The sun, lithium-ion batteries, or any power bank? Yes, batteries. So yes, when we talk about energy storage, we're mainly referring to the capture of energy, right? So there's several ways of getting this energy. That can be radiation, electrical, temperature, chemical, and more. Let's see how this goes. San Elmo is still around. And the first place, it's quite close. It's quite high. Let's continue. Question 7. Almost getting to the end, guys. So, what causes earthquakes? The movement of the moon, wind, or the tectonic plates? Yes, very well. So yes, as you guys heard, earthquakes are caused by the heating and cooling of the rock below the tectonic plates. Let's see, what do we have here? Okay, not major movements in the... Oh yes, Sara Calegaro moved up. Okay. Question 8. Okay, so why would it be important to make predictions of disease? So to forecast any disease, to identify a disease, or maybe to eradicate a disease? Yes, actually, it's mainly to forecast the characteristics of a disease, not precisely to eradicate it. So what we want is to mainly characterize a disease to aid public health and create any mitigation plans for the future. Okay, so Jones is still on top, but then followed closely by St. Elmo. Question 9. So, can hydrogen be used as fuel? No. Yes. Or only when combined? And the answer is yes, of course. You guys paid attention very well. So yes, hydrogen can be used as an internal fuel for combustion engines. Okay. Next question, 10. So, can people cause earthquakes? So no, sometimes, or maybe yes. So yes. I mean, so yes, but this mainly be caused by activities such as mining. So yes, it's humans through something else. Sometimes. We can count that one as good for them.
Who's leading?
Very well done, Pingu. Okay, so this is an open question, so feel free to drop any word that you guys think. So, what are examples to inform people about any new disease? How do you inform, or how do you let people know that there's new diseases around? Just an open question for some fun. Oh, sorry. I am not so sure if anybody is dropping any comment, but as we cannot see it in the screen, I mean, we were thinking it was supposed to appear some words in here. Ah, there they are. So yes, exactly like that. TV, social media, social network. Yes, just by talking to people. So yes, there's also things as podcasts. I don't see them around, but of course there's so many different things that we can use to communicate stuff around, right? So let's continue. So question 11. So are earthquakes common in Norway? So I'm waiting. So yes, no, or kind of, meaning sometimes. So apparently, so yes, the answer is. Well, kind of. It's a synonym for it depends. So yes, we're using kind of as a synonym of it depends, because yes, so small earthquakes can happen like far from plate boundaries, yes, but also in these mid-ocean ridges. So yeah, that's the case of Norway. So yes, it depends. Okay, any changes? Oh, nice. Bill and Peseg went up. Okay, question 12. Okay, how long has coronavirus existed? So 1 year, up to 55 million years, or around 1,000 years. So yes, up to 55 million years, some studies said. And of course, when we say coronavirus, we mean the whole family of these viruses. So yes, it's been around for a really long time. Okay, St. Elmo is back. Okay, almost the last question. So, what is the largest earthquake ever recorded in Norway? 1904, 2020, or 2012? So, yeah, this was new for me too. I thought it was the one from 1904, but then there was one in 2012, apparently in the Jan Mayen Island, and that was one 6.6. And this island is actually Norwegian territory. Okay, so no changes in the board. So, last question. Oh, there you go. Do you guys know how or what's the percentage of fully vaccinated people in Norway for COVID-19? So around 70%, 90 or 40. So yes, around 70% of the people has been fully vaccinated, almost everybody. And that was a quiz, guys. Let's see who won. Yes, so Beyonce, please. Congratulations. Oh, sure. Yes, we can give you a clap here in front. Well, the prize, we don't have it with us. But congratulations. But we can actually get your data, like your information, and we can send the t-shirt for you. Thank you. Thank you, everybody, for participating and for coming.
Yes, there you go.
Just an information that we, it's not confirmed yet, so it's secret information, stream on YouTube. No, whatever. We're in negotiation for next event, the 16th of November, so just stay tuned on the social media, website, newsletter to have the information and yeah, everything. It's really
Follow us.
follow us. Yeah, you as well on the streaming. But yeah, thanks everybody for coming. Hope to see you again. Have a drink, enjoy melting, not melting, mingle. No, that's fiction, very melt. Mingling, thanks. Thibaut out.